Hi guys, Mr. Rocco here. Hope you had a good weekend and are enjoying the snowfall that is happening right now as I record on a Sunday morning. Let's jump right into the next part of the unit on weather, and this video is going to be talking about the wind and wind belts, planetary wind belts. So the definition of wind is the horizontal movement of air on the surface from high pressure to low pressure. Again, wind goes with the surface. That's why it's horizontal. If this, let's say this is the ground and the air is going up or down vertically, that's not called wind. Actually, that's called updrafts and downdrafts, which is all part of convection, right? Remember, convection is this circular motion of air, but that's a vertical motion. But wind is going horizontally, so with the surface of the earth. Again, wind always goes from a high pressure system, leaves the high pressure, goes out from a high, and goes into a low pressure system. So it goes from high to low. And this shows that in this side view. So again, high pressure, high rhymes with dry. And again, you have dry skin and drier conditions typically in the cold weather in the winter, right? And so high pressure tends to be your very cold, dry, heavy air. So over here on the left is a high pressure air mass. Over here on the right is a low pressure air mass. Low pressure is the complete opposite. Instead of cold and dry, low pressure is warm and wet. So it's moist, humid air. Less dense. Remember, low pressure air is less dense. And so when you have two different systems, a high pressure system and a low pressure system, that creates, and again, we touched on this last week, what's called a pressure gradient. And if it's a strong pressure gradient, which means this high pressure over here might be, if I'll throw a number on it, 1020 millibars. Okay, that's very cold air. Over here on the right, your low pressure is going to be a storm. You got moisture, it's warm, it's wet, it's muggy. This might be 980 millibars. And so you've got a difference there of, 40 millibars, right? If you subtract 1020 minus 980, gives you a 40 millibar difference. That's a lot in the world, again, of weather. 40 millibars is a lot of pressure difference. And so that creates a strong pressure gradient, and it's going to generate wind. The wind will blow from the high pressure toward the low pressure. Always from a high toward a low. This shows something similar, although we haven't talked about these yet. This is, you have a front down here. A front is just a boundary between two different air masses. So here you have cold air, which again is high pressure, on the left. You have warm air, which is low pressure, on the right. And it's the cold air that's pushing in toward the warm air. And if you go back to density, right, cold air is more dense than warm air. So the cold air has a very easy time at causing this warm air to lift. And that's what you're seeing here is a front. This is a cold front with these little blue triangles on it. And we'll get into that in another week or so. And you have what they call it, meteorologists will call that, it's a frontal lift. And that's what's happening. The cold air, this cold front is lifting the warm air right up over top of it. And so this warm air is getting pushed right up over the cold air. And again, this is all stuff we've talked about. As the warm air rises, that's when it starts to go through the process of forming a cloud. So it rises. I'm going to write these with a mouse. Sorry. After it rises, it expands. And again, the reason it's expanding is because the air, as it's rising up higher into the atmosphere, way up here in the upper parts of the atmosphere, there's less pressure up here. So the air molecules aren't staying close together like they are down here on the surface. They have room to breathe, so to speak. They can spread out. And so when the air gets up here in the higher parts of the atmosphere, the air molecules can move further apart from one another, less collisions, which causes less friction, less heat. And so it expands, it cools. And once it cools to a certain temperature, and we'll get into that in another video this week, it reaches what's called the dew point temperature. Dew point is when the air is saturated, and then it goes through the process of condensation. So it rises, it expands, it cools, and then it condenses. And once it condenses, you're turning this air, which is a gas, right, back into a liquid, and that's what makes these clouds. And so all of these steps, which are very important, make sure you know them in that particular order, is the process to make a cloud. It has to rise, it has to expand, it has to cool, and it has to condense, all to form clouds. Now, if the Earth didn't spin, right, if the Earth didn't rotate, like I said, winds always go from a high to a low. So notice the arrows. These arrows are supposed to represent winds. This is the center of a high pressure. The winds are going out from a high pressure. In a low pressure, they're going in. Notice all the arrows going in. So it's high to low. That's if the Earth didn't spin. These arrows would go straight out. The winds would go straight out from a high and straight into a low. However, now we have to go back to astronomy, when we covered astronomy a while ago, and we had an effect called the Coriolis effect. The Coriolis is due to the Earth's rotation. It causes objects, let's say this is the Earth, objects in the northern hemisphere curve to the right, objects in the southern hemisphere curve to the left. Well, that's going to now take effect when we're talking about high and low pressure systems. So a high pressure system, and this is just for the northern hemisphere, so I'll put NH. In the northern hemisphere, where we are, United States, high pressures, the winds not only come out from the high, like I showed you here on the top part, but now you have to put a slight right-hand hook on that. So they come out and they curve to the right. So this arrow's going to the right, this one's going to the right, come out and always go to the right. So when you look at a high pressure system in the United States, the circulation, they call that, the wind circulation, is out and clockwise. See how they're going in a clockwise fashion, out and clockwise. The nice thing about highs and lows, they're complete opposite. So I usually tell students every year, focus on a high pressure. If you know the way the winds go around a high pressure, low pressure is just the opposite. So instead of out and clockwise, notice in a low pressure, these black arrows, they're going in and counterclockwise. So a low pressure, which again is a storm, low pressures are going to be tornadoes, low pressures are going to be hurricanes, low pressures are going to be nor'easters, when we have a nor'easter, right? It's a big snowstorm. Any kind of storm system is a low pressure. The winds always spiral or circulate inward and counterclockwise. So again, focus on a high. As long as you know the winds go out and to the right, because of Coriolis, that's out and clockwise. Low pressures go inward and counterclockwise. So that's what this slide says. Winds around a high circulate clockwise. And you can see that in this picture here. They're going out and clockwise. Winds around a low pressure, and again, this is only in the northern hemisphere, go inward and counterclockwise. So out and clockwise around a high, inward and counterclockwise around a low. Now, this little trick, I've been using this for quite a long time. This will help you remember the high pressure and the way the winds circulate. So let's say you had to go to the doctor for a checkup, and you're waiting in the waiting room, and, you know, the doctor comes in, and the doctor says, "Hi, how are you?" And you say, "Hi, doc." That high doc is standing for something. The high stands for high pressure, and the doc, short for doctor, right, DOC, has meanings, 3 of them, and I wrote it down here. So high is high pressure, and the DOC stands for which way the air circulates around a high. Now remember, high pressure air is cold air, right? And what is cold air? More dense. And what does more dense air do? It sinks, right? It's heavy. Cold air is heavy. So it sinks. That means it goes down, right? It's up in the upper parts of the atmosphere, and it drops down to the surface. So the D is down. The air goes down. And then the O stands for it goes out. Because remember on the picture I showed you a minute ago, it goes out of a high pressure, and then it curves to the right. That's clockwise. So you've got high doc. It means high pressure. The air goes down, out, clockwise. So that's where the doc part comes in. D for down, O for out, C for clockwise. If you remember high doc, then a low is the opposite. So low pressure would be opposite of down would be up. Opposite of outward would be inward. That's I. And opposite of clockwise would be counterclockwise, which has 2 C's in it. Doesn't really work with a word because it spells Uick. So low is Uick, which really is nonsense. But if you remember, like I said, high dock, that'll help you to remember low pressure. So high dock, down, out, clockwise. Just keep saying that to yourself and repeating it in your head till it sticks. High pressure, high dock, down, out, clockwise, down, out, clockwise. Good. This we went over last week. It was on some of the homeworks from last week. So when you're looking at a weather map, and again, you see a big blue H for high pressure, and you see a big red L for low pressure, and they're fairly close to one another. In between, especially around typically the low pressure, you're going to see a bunch of isobars. Isobars are lines that connect equal pressure. If the isobars are very, very packed together, like they are, you see here, that means a strong pressure gradient. So the closer the isobars, the bigger the difference in pressure. That's what they mean by pressure gradient. Big difference in pressure between two systems that are close to one another. And so the isobars will be closer together, which indicates a very, very fast wind, strong wind. If you had a low pressure like this, let's say over on this side, but the isobars, let's say that's 1, and the next isobar was way out here, like much, much further apart, then not as windy. So this storm would have, over here on the right, would have a lot of wind. This storm over here on the left would have very little wind. Right? So just looking at the distance between the isobars will tell you whether it's going to be a windy day or not a windy day. So here's a typical map. I pulled this right off the Weather Channel. I'll give props to the Weather Channel so I don't get any copyright issues. And you can see here is a typical what happens in the winter. We get a snowstorm like we're getting today on Sunday. And so your storm is going to, and we'll get into this down the road here, the storms tend to move in the United States toward the northeast, which is one reason why they're called nor'easters. So they head northeast. So as this low pressure moves off to the northeast, notice these isobars right in here, how they're packed together. The reason they're close is, I can see it's up at the top of the map, right up here in Canada is an H, so there's a high pressure. So what's going to happen is this high is going to slide down this way. This low is going to keep moving this way up to the northeast. And so in between this high pressure over here and this low pressure over here, you've got packed together isobars. So there's a strong pressure gradient between these two systems, and that's why you see these white circles, these white lines going around the low, are showing you that it's a strong pressure gradient, and you have a lot of wind. So there's a lot of wind over here behind the storm, which is very common for snowstorms, right? We'll get snow over here, Rhinebeck's in this general area. We'd get the snow, and then the next day, especially if it's a light, fluffy snow, you get the blowing and the drifting of the snow. Notice over here in the southwest part of the United States, California, Arizona, a place like that, you don't see any packed together isobars. So on this particular map, right, if you looked at it right away and quickly said, hey, where is it windy in the United States today? Oh, it's windy over the Midwest and the Northeast, New York. Is there a lot of wind out here out west? No. How do you know? Well, the lines aren't close together, the isobars. So that's a quick way of analyzing a weather map for wind. So this is just a map I drew. So it says, between which two letters are the fastest wind speeds? So you've got A, B, C, D. Where's the fastest wind? Hopefully you're going to tell me it is C to D, right? Notice over here the isobars are close together, and that's behind that little blue box. Yep, C to D would be the fastest winds because you see the isobars are packed. All right, planetary winds. So actually in your, don't worry about this where it says pass out blank diagram. You don't need to do that. In normal school, I would pass out a blank diagram. We draw the winds, but actually the wind belts are listed in your, or there's a map, I should say, in your ESRT. So as you're, maybe pause the video and grab your reference table and then go to page 14 in your ESRT, and you will see the planetary wind belts as a map of the world, a globe map that shows you the wind belts. So planetary winds are, if you ever heard the term jet stream before, the jet stream is what controls the path of storms. So it's like a road for a car, right? A car is going to follow the road and stay on the road. You don't want to go off-road. That would be a bad day for the car. Storms do the same thing. Their road, in air quotes, is the jet stream. They have to follow these wind belts, these prevailing winds, and that's what the storm will track. It will take the track of the storm. Planetary winds are between Earth's pressure zones. Earth is kind of broken up into sections, 6 of them in particular. There are 6 planetary wind belts. And again, I recommend to you, as you're watching this part, go to page 14 and you can follow along and see the wind belts, and I'm going to kind of break down that picture on page 14. And actually, let me show you this. This is kind of cool. It's an animated map of the global wind. This is actually current, and maybe I'll put this link on Canvas. So you can click on this at any day, and it's going to show you the exact current weather and where the flow of air is, the wind belts. So if I click on this, it should work. Yep. So it's going to pull up this website, and I'll throw this on Canvas so you can look at it. You click this little Earth right here, and give it a second to load, and all of a sudden you can zoom in and out. Focus on the United States. You can rotate the Earth, which is kind of cool. I'm going to zoom in more. Now remember, today's Sunday. We have a storm off the eastern seaboard, and you'll actually see it. It's a low pressure. And remember, a minute ago we said winds go counterclockwise around a low. So if you look at the east coast United States, can you see that counterclockwise? You can actually point to exactly the center of the storm, where the actual spin is, the rotation on the eastern seaboard. And I'll put the mouse right over it. It's right there. Let me zoom in a little closer if I can. Yeah, let's do that. You see the storm would be right here. These are showing you the winds circulating, and you see that counterclockwise flow around the low. So this is where the storm is actually right now. Now it's, what time is it? And it's 12 o'clock. So it's noon on Sunday, and the storm is just getting going and starting to come up the eastern seaboard. I believe Long Island, New York City is getting heavy snow right now. And I'm looking out my window. Yeah, we have some snow, not heavy. It might pick up a little bit later today, but the storm is right here. That's the center of the storm, and this storm is going to start heading in this direction. It's going to start heading north and east and head off the coast of Cape Cod. Cape Cod's right in this area, Martha's Vineyard, Nantucket. So that's kind of cool. This you can click on this any given day. I'll put this link on Canvas. Now if you go, I'm going to zoom back out and go out here to the Pacific Ocean, you can find another storm. This will be a storm coming, I think, for us later in the week. Right over here. Let me zoom in the Pacific Ocean. I love this website. This is kind of cool. See that storm right there? See how it's going counterclockwise, spiraling? That's another low pressure system right there. That storm's going to start pushing this way, hit the west coast, California, and then eventually come in our direction. But that's kind of cool how you can see that. And you can rotate this thing anywhere. You can go out. We can zoom out and go over to Europe. Let's see if they're getting any storms. Give it a second to load. Yeah, let's see. Sometimes hard to spot the circulation, the counterclockwise. Yep, there's one right here. So this is what, you got England, Ireland, right? The UK. Here's a storm right here off the coast of Ireland. Probably heading toward in that direction. So they're going to get hit with some kind of storm, whether it's snow or rain, but there's another storm there. So you can just look for low pressure systems, storms, which is really cool. I'll put that on Canvas. Okay. Now, when you're talking about high pressures and low pressures, let's go back to that trick for high pressure. High was high dock. So that means the air goes, again, downward, outward, clockwise. Down, out, clockwise. There's another name for a high pressure system. It's called an area of divergence. Think in math class, the word divide, what does divide mean? Split, right? If I gave you the number 10, I said 10 divided by 2. What does that mean? That means take the number 10 and divide it into 2 parts, right? 5 and 5. So 10 divided by 2 means to create 2 different pieces, each 5 and 5, right? So divide means to split. So that's what diverge means, to split. And you can see it in the arrows here. So a high pressure, and this goes back to the high dock, down, out, clockwise. Because again, remember, high pressure air is cold and it's dry. And so what happens, this is your winter air, right? Cold and dry air. It's going to be heavy, so it's going to come down and go out. Down and go out. They split apart. See how the air, these are showing you two different streams of air. So you've got a stream of air here and a stream of air here. This one's going down and out to the left. This one's going down and out to the right. And so when you have divergent air, a high pressure, remember high rhymes with dry, you're going to have certain latitudes on Earth in particular that are going to be your drier climates. Those are the 30s and the 90s. So 30 degrees north and 30 degrees south, and 90 north, 90 south. Now 90 north and 90 south, you should know, are the poles. Which right away then kids will start thinking, like, what do you mean by that? That means the North Pole and the South Pole, because it's extremely cold, is also extremely dry. They do not receive a lot of precipitation at the poles because the air is so cold and so heavy, and it's always sinking. If this hasn't stuck yet, I'll go over it again. Clouds only form when the air does what? Rises and expands. Sinking air, you do not form clouds in sinking air. Well, cold air is always sinking, and that's why it's a drying process. And so dry zones are going to be where the air sinks. That's going to be your 90s and your 30s. Now, 30 north happens to be, if you look on a map or on a globe, 30 north happens to be the biggest desert on Earth, which is the Sahara. So if you go to the Sahara Desert, right, over in Africa, that is sitting right at 30 degrees. Right, so that is one of your larger deserts. If you go to 30 south, look on a globe, look on a map, 30 south latitude in the southern hemisphere is the Great Victoria Desert. The outback of Australia sits at 30 degrees south, which now hopefully makes sense to you why they are where they are. Right, the Sahara and the outback in Australia aren't just randomly placed in certain places on the earth. They're there because those areas are divergent zones. They are high pressure dry zones where the air is constantly sinking and diverging, moving apart from one another to create dry climates. All right. Now the opposite is not divergence, it's called convergence. Converge means to come together, right? Con meaning with, right? And verge, move with. So now instead of a high pressure, you're talking about a low pressure system. Two streams of air come together at the surface. So instead of the arrows going down and out like this, the arrows go in and up. So this would be the surface right here. The air is going to come in at the surface. This is your warm air, and then it's going to rise, come in. This air is going to come in toward the other one. They're going to meet, and then it's going to come toward each other and then go up. And again, rising air is where you form all your clouds, because once it starts to rise, it goes through all those steps we talked about earlier. It's going to expand, it's going to cool, it's going to condense. And so you have, again, specific latitudes on Earth where that happens. One happens to be 0, the equator, right? The equator tends to be hot and rainy and sticky and humid, and it's a very wet climate. And your 60s, 60 north and 60 south. 60 north in particular, again, if you look at a globe, you can correct me if I'm wrong, but I believe 60 north happens to be up in the Scandinavian countries. You have Norway and Sweden and Finland. And if you follow anything with the Olympics, right, especially the Winter Olympics, Norway, Sweden, and Finland happen to be very excellent countries when it comes to the skiing events, all the alpine events, ski jumps and downhill skiing, because of the fact that they are a wetter climate and also cold. So they get a lot of snow in Norway, Sweden, and Finland. And so they tend to do very well. They get snow, I wouldn't say all year, but pretty much a big chunk of the year. It snows up, especially the northern parts of Norway, Sweden, and Finland. They could have snow quite a few months of the year, majority of the year. So convergent zones are going to be wet zones, whereas divergent zones are going to be dry zones. This is the planetary wind map, and what I did is I turned it sideways. So this is in your reference table on page 14, and I turned the globe sideways so you can see convergence and divergence. The nice thing about the ESRT, it tells you where it's wet and dry. So I went over that just now, wet and dry, but the reference table will tell you where it's dry and wet. So you never have to memorize that. So I highlighted in yellow on this where the wet zones are. So here's 60 north up here. Here's 60 south. It says wet. And it also says wet at the equator. Sideways, but you can see that. So again, if you look at your reference table, you'll see that. Then you have your dry zones. It's dry at the North Pole. It's dry at the South Pole. It's dry at 30 south. And it's dry at 30 north. And then in between are the wind belts, which we're going to go over here in a second. This on the side these are convection cells. Remember we talked about convection, right? Hot air getting pushed up, cold air sinking. So you've got a convection cell. This is one here. Here's another cell, another cell. Each of these is a convection cell. And it's how the cells are moving will tell you whether you have convergence or divergence. For example, I highlighted the equator one here for an example. This convergence cell right here, I'll label this one number 1. I'll label this one to the left number 2. So if you look at convection cell number 1 over here, this is going clockwise. This cell is going counterclockwise. This would be the surface of the Earth. And you have right here a convergent zone. Remember I said convergence looks like this. In and up, coming together. Notice the convection cells. Because this one's going clockwise and this one's going counterclockwise, when these two streams of air at the surface meet, right? Notice they come in toward each other and then up. That again, that rising air right here is going to create clouds. The rising air is going to expand and cool, and there's my cloud, and you'd have a lot of rain here. And that's why the equator tends to be a wet zone, because of this convergence right here. Now, once you leave the equator and go to the next latitudes on opposite sides, go 30 north, 30 south, notice what happens. This, let me clear this so it makes sense. So this, we'll call this number 1 now, and this cell right here, number 2. Well, this cell again is going counterclockwise. This cell's going clockwise, this convection cell. So what's happening here? Well, when you get to the boundary between them, this cell's going down, hits the surface and goes out. This cell's going down, hits the surface and goes out. So right in this section, right here, put an X, that's a divergent zone, because remember divergence is down and out, down and out. So here you have divergence. That creates a dry zone. So hopefully you can see that from a side view. This is converged, they're coming together and then lifting off the Earth's surface. And over here they're coming down and leaving each other and going apart from one another. So anytime you see those convection cells, you'll see they're going in opposite directions. Same thing over here. If you look at 30 north, this one comes down and out. This one comes down and out. So they're leaving each other when they get to the surface. That's why you have a dry zone, divergence. So it really just alternates, right? This is converge, then on opposite sides, diverge, diverge, dry, dry. Then it goes back again. This would be converge, this would be converge, wet, wet. And then it alternates again, diverge, diverge. So it just they kind of flip-flop. This will come up from time to time. I'm trying to think if it'll ever come up on a regions. It might. So a high pressure zone has another name. It's called an anticyclone. Right? Cyclone would be a low pressure. So when they put anti, right, meaning opposite. So if you see that in a question, just don't panic. An anticyclone is also another name for a high pressure system. And again, down and out. Down and out is divergent. The air goes down, out. Just remember the high dock. Down, out, clockwise. Down and out is the divergent part. So that's the winds around a high. I think one of the assignments this week, I will give you I think I gave you a blank, it'll just be an H, and I ask you to draw arrows. You can even use your mouse or whatever, the draw tool, and try to draw arrows. So this is how you want to make the arrows. Remember, you're going to go out and clockwise because of the dock, high dock, right? The ock part of dock. So out clockwise, out clockwise. So I think I asked you to draw like 3 or 4 arrows around a high pressure to show the wind circulation. So that's going high pressure, down and out and clockwise. You're not seeing the down part because this is 2-dimensional, but you can see the out and clockwise part. And then a low pressure, which sometimes is called we call them tornadoes. Other parts of the world do call tornadoes. They call them twisters. They're called cyclones. So some parts of the world will call a cyclone a tornado, which is a low pressure. The winds are going up and in and counterclockwise. So going up and in and convergent. And so here's the winds going around a low pressure. And again, I think I did that on one of the assignments this week. I think it's on a worksheet called Pressure Worksheet. You'll have a low pressure. Just put the winds going in and then kind of counterclockwise. Going in and counterclockwise as you go around the low. All right, it says, which way would the winds blow if the Earth didn't spin? So again, always from high to low. So if the Earth did not rotate, there's always cold air at the poles. So you have high pressure is cold air up here at the North Pole, and you'd have high pressure at the South Pole. And the middle of the Earth is the hottest, right? Strongest sun, perpendicular rays. You've got low pressure at the equator. Winds would just basically blow down from the poles. They'd come from the poles and head toward the equator. You'd have two wind belts, one in the south, one in the north. But because the Earth does spin, now we have to throw Coriolis into the equation, and that's what changes things. We take two wind belts, and we're going to turn 2 into 6. And again, this is on page 14 in your reference table. So again, I recommend you looking at page 14. You'll see the 6 belts. They are broken up every 30 degrees. So you've got the equator at 0, and then 30 north, 60 north, 90 north. And then down here, 30 south, 60 south, 90 south. So you've got your 6 wind belts. I'm going to start at the top, and we're going to work our way from North Pole to South Pole. Now, this is also on that reference table. It tells you that, again, it's dry at the 90s. So you see there's dry air here. Dry rhymes with high. You also have dry air at the South Pole. There's another dry zone. Remember we said the 30s are dry. So high pressure is dry. And at the 30 south is dry. And then your 0 and your 60s are wet. And it really just alternates. So you tell kids, start at the North Pole, and just remember that this is dry, and then it goes dry, wet, dry, wet, dry, wet, dry. Just flip-flops. Same thing with your high pressures. Dry is high, so it goes high, low, high, low, high, low, high. If you start at the top, it makes it easy. Just keep alternating. Now, to draw the wind belts, and again, they're drawn in the reference table, but this is how they draw them, because students will say, Mr. Rocco, how do they draw these things? And a couple of rules. One, remember that winds always go from high to low. That's important. And in the northern hemisphere, winds curve to the right. In the southern hemisphere, winds curve to the left. If you can remember this little bit of information, it's not a lot to remember, high to low, and then right and left, that will help you draw the wind belts. So let's get into them. So we're going to start with up here at the top. We'll work our way down. So in this first section, right, if it's high at the North Pole and low at the, high at 90 and there's a low at 60, winds have to go from 90 towards 60. So they're coming down from the poles. Now, this is where it's a little tricky. Whenever the winds are coming from the north, like this, and remember the northern hemisphere, the winds curve to the right. And again, I call this a stage effect. A person on stage moves to their right. It looks like the audience, they went to their left. These winds are going to the right. They're coming down from the North Pole, and they're curving to the right. And what I did is over here, if you look, I took the Earth and I flipped it upside down. So NP, this is the North Pole. When they leave the North Pole and they go towards 60, that is curving to the right. But then when you turn the Earth around and make it look the way we see it, especially from space, that is to the right. So anytime a wind comes from the north, right looks like left, or left will look like right. So like when we get down here to the southern hemisphere and it says, oh, curve to the left, but it's coming from the north, this is going to be to the left. And again, sometimes students say, Mr. Rocco, you don't know your left from your right. I'm like, well, yeah, actually I do. I do confuse it from time to time. But no, when it comes from the north, to the right looks like left. And when you're in the southern hemisphere, to the left looks like it's going to the right. You almost have to, like I said, flip the Earth upside down. So that's the first wind belt. It's going to come down to the right, high to low. let's take this one before I show it. What would it look like, right? If this is a high at 30 and this is a low at 60, it's going to head from high to low. So it's going to go up. It's going to head north and curve to the right. So they're going to go like that, right? Up to the right. When they come from the south and go north, then it's normal. So that's that belt. So I drew a bunch of them just so you can see that. Then we'll go to this one. I'll kind of predict, right? This one is going to look just like the first one. It's going to go down, and again, right's going to look like left. So they're going to go like this, high to low, and to the right. So it's going to look like that. And again, if you're looking on page 14 in your reference table, you'll see I'm drawing them, hopefully, the correct way. Let's go to the next one. Now we're in the southern hemisphere, so high to low. It's going to leave 30 and head toward the equator, but left is going to look like left, so it won't have to flip it upside down or flip it reverse. It's going to look like left. So that's the next one, high to low, curving to the left. This is the one, again, it's going to be a little tricky. You're going to leave 30, go towards 60, but left is going to look like right because they're going to go this way. That is to the left because you're standing at 30 watching the wind leave your feet. Let's say it's going away from you, so you'd be looking toward the 60 and you're seeing it go left. So it looks like that. And then the last one, this one looks like this one. So these two match. Same thing up here. These two match. Whatever this one is the same as that. Whatever this one is the same as that. So this is going to come up from the South Pole and look like it's going to the left, like that. And when you're all said and done, you get this, which again, now you should see that on page 14 in your ESRT. Now, there's names for the winds. I wouldn't get too hung up on memorizing the names, but you should know, and I think I mentioned this. If not, I'll mention it again. Winds are always named for the direction they come from. So if I said, hey, draw a north wind, that's a north wind. Or, hey, draw a south wind, that's a south wind coming from the south, going the opposite. Hey, draw a northwest wind, that's a northwest wind. Hey, draw a southeast wind, that's a southeast wind. So you always draw it, start the direction it's coming from and go in the opposite direction. So if you name these, right, these winds up here are coming from kind of the northeast. So that's what they're called. They're called the polar northeasterlies because they're coming from the poles heading from the northeast going southwest. This is our belt right in here. Very important one. This one you should know. We sit in what's called the prevailing southwesterlies, or just the southwesterlies. The winds come from the southwest, and everything heads northeast. Now, if you remember when I showed you that map, the Weather Channel map, and I was showing you that low pressure, right, and I said everything goes northeast. This is why. Because we're stuck in a wind belt. We are not stuck, but we're in a wind belt, I should say, that goes from southwest to northeast. And that's why sometimes winter storms, you'll hear they'll say, here comes a nor'easter. Well, why is it called a northeaster, a nor'easter? Because that's the way it's heading. It's heading in a northeast direction. So they call them nor'easters for that reason. Then you have your trade winds, which goes back to the days of trade with the old world and the new world. And so you have the northeast trades, because they're coming from the northeast. And you have the southeast trades, because they're coming from the southeast. Notice both of them are coming from generally the east, heading toward the west. That's what carried ships back in the day. So your trading ships and all your ships that used to leave, actually even your slave ships that came from Africa and places like that. And I'm not a historian, but you know, that's where you got your slave ships, and you've got your trade ships that came from the old world, right? England and France and places like that. Spain, they got caught in these trade winds, and that's what carried the ships across the Atlantic Ocean toward the New World, toward the United States, toward North America. It's getting messy. Let's clear that. All right. Then you have your prevailing northwesterlies. So these are both prevailing, except ours come from the southwest. These come from the northwest. Go that way. And then remember, these were called polars. These were the polar northeasterlies. These are the polar southeasterlies, coming from the southeast, heading northwest. So again, just as long as you remember, winds are always named for the direction they're coming from. And then you have your, I'm going to skip that. Let's go right to this. So they label they don't say prevailing or polar, they just tell you the direction. So you see up here, they say NE. So they're telling you those are northeast winds, right, coming from the northeast. We sit here. The United States is in between 30 and 60, right? So this would be us here, the United States. So we're in the SW. We're in the southwest winds going northeast. Below us are the northeast winds coming that way. You got your southeast winds, you got your northwest winds, and you got your southeast winds. Okay. So this is in your reference table. Again, it shows you the dry zones, right? The 30s are dry. The poles are dry. I know some questions on the worksheets this week will ask, where is it a dry zone? Where is it a wet zone? So use this chart to help you with the homework. You got your wets at 60. There's another wet at this 60 and the equator. Where's the convergence and the divergence? Remember, dry and divergence go together. So this is a divergence. Why? Because this comes down and out. And this convection cell, remember, came down, hit the surface out. So that's a divergence. Just remember D, dry. And over here, this one, down and out, down and out. So that's another dry zone, divergence. And again, wet is convergence. So use this map to help you with some of the questions on the homeworks this week. Planetary winds also, well, the winds will actually create the ocean currents. So that will come up. They'll say, what causes ocean currents? The winds and the planetary winds. And they also curve to the right in the north or the left in the south, depending on which hemisphere you're in. And there's a map actually in your reference table. This is it. It's on page 4. This is the ocean current map. It'll say surface ocean current. They give you 2 types of arrows, a white arrow or a black arrow. If it's a black arrow, those are warmer ocean currents, which is obviously going to affect your coast, right? Think it's common sense. A warmer current will bring warmer weather, keep your temperatures above freezing. A cooler current is going to keep your coastal cities at a cooler temperature. So you can easily see, and again, this is a kind of a fuzzy map. It's not that nice and crisp and clear. If you look at the one in your ESRT, you should hopefully see a little bit better. But I just wanted to point it out to you. Along the east coast of the United States, right here, I use blue. So this is us. There is the Gulf Stream, which you've probably heard of. The Gulf Stream is a warm current. Why? Well, makes sense. It's taking water from down here. This is near the equator, right? This red line's the equator. You're bringing warm water up the eastern seaboard, and then here's that Coriolis. It's curving to the right. This is the one that's very important for hurricanes, to stay a hurricane. So when a hurricane is coming from Africa, and that's where they come, over here, they start off the coast of Africa, they get caught in these warm currents that push them to the west. They come from east to west. They then take that turn when they get to Florida, and then they do that right-hand hook. If they stay in this Gulf Stream, they tend to stay strong. The problem with a hurricane is all they have to do is move a couple hundred miles this way. If they leave this, let's say this blue line represents the Gulf Stream. If they come out here a little bit and go a couple hundred miles east of the Gulf Stream, this water out here is extremely cold, and that's it for the hurricane. It fizzles out because hurricanes need warm tropical water. So it's a very narrow path of warm water, but if the hurricane leaves that little narrow channel, it'll fizzle and die. So there's a nice warm current coming up the east coast, which keeps the eastern seaboard obviously much warmer. You go out to California, and I've never been personally, but I have many students that go out there and say, oh yeah, Mr. Rocco, I go, I said, you ever go in the water? And like, oh, it's chilly. Yes, because the California current is a cold current. So out here, you'll see a white arrow on the map. This is water coming from Alaska Bay, way up here, or near Seattle or Vancouver, Canada. It's coming down the west coast of the United States. And again, when it comes from the north, see, it is curving to the right. So there's that Coriolis again, stage effect. It's curving to the right. It's bringing cool water along the west coast. And so California water, I just tell students, right, I've never been, but I can pretty much guarantee you, the California water here is much cooler than Florida water. Right? Florida water temps can get into the 80s, maybe even touch 90. California water, especially or anywhere up and down the west coast, like Seattle, Oregon, you're talking 50s and 60s. Maybe gets to 70 if you're lucky, but it's very cool water along the west coast of the United States. And then if you go down here to South America, you get the same idea here. Along the west coast of South America is also a cool current. It's called the Peru Current. It brings cold water from way down by the South Pole near Antarctica and pumps that cold water up along the west coast of South America. And again, you see that curve to the left, right? Opposite Coriolis, curving to the left. That's going to keep the west coast of South America cooler. You've got your glaciers, you've got Argentina, Peru. That's why it's called the Peru Current. Those are colder climates. Those are colder countries. You go to the other side of South America, and you have the Brazil Current. That's a warm current. So again, it's like the Gulf Stream. It's bringing warm water from the equator and pumping it south. And again, it's going to curve to the left, but it looks like right. That's what's going to hit places like Rio de Janeiro. So if you go to the beaches of Brazil, the coast of Brazil, it's going to be a warm tropical kind of climate where the water is the climate is much warmer. So I just wanted to point that out to you. And let's see, this is showing you the path of Katrina. So if you go back to 2005 when Katrina hit, you can see how these wind belts and ocean currents can steer the path of a hurricane, especially the winds. So Katrina came across the Caribbean, South Florida. It was caught in the trade winds because right here, this red line is 30 north. So if you remember from the planetary wind belt, these are the trade winds. So most of Florida is actually in the trade wind belt. The rest of the United States is in the southwesterlies. And so hurricanes will come across from Africa. They'll get caught in those trade winds and the ocean current that's also pushing this way. And they'll come across, and that's what Katrina did. And then it went into the Gulf. It hit very warm water, blew up into a Category 5, a high Category 4, hit New Orleans. And then this is very typical. Once a hurricane gets to 30 north latitude, it could be here, it could be off the coast of Florida like Jacksonville's right about here. It all of a sudden switches wind belts. It goes from these northeast trades that were pushing it toward the west and now getting caught in the south west wind belt, the prevailing southwesterlies, that turn it and go the other way. And now it's going, instead of going south and west, it's going to start to turn and go north and east and head out off the coast of North America, Nova Scotia, and head out into the North Atlantic. And so that's typical of hurricanes. They take that right-hand hook, and that's because of these wind belts that steer them in that direction. And I think this is the last slide, just showing you the Gulf Stream. So these are water temperatures. I don't know if you can make out. This is the eastern seaboard. Here's Florida down here. And this red, bright red, is that really warm water that came from the equator down in this area. Oops, I'm trying to use a different color than red. Yeah, so the hot, warm water from the equator is getting pumped up in this Gulf Stream. And again, if a hurricane stays right in here, it's going to be good to go and stay strong. It's when it jogs out this way a little bit and gets out into this part of the Atlantic, you see the greens are going to be cooler temps, and especially when you get into blues and the purples and pinks, those are going to be your much colder ocean water. But the Gulf Stream, you can see that really warm little narrow channel that rides up the eastern seaboard. Keeps those hurricanes strong. Okay, I know that was a long video. There's only going to be 2 videos this week, so please make sure you watch the whole video and use some of this information, obviously, to help you with the assignments. And I will talk to you soon.